Hi and welcome to Behind the Scenes of an Apple IIGS demo. My handle is Jesse Blue and I am the programmer of the German group Ninjaforce. We started on the 2GS in the early 90s and released a number of programs which you can find on the web. We are most known for the Ninjaforce Mega demo, released in 1995, the graphics and sounds of Wolfenstein 3D for the 2GS, and the Bomberman game Kaboom, which we finished only in 2015. This year we released a new demo called Kernkompetenz at the Revision 2017 demo party. Kernkompetenz was our first production that was not developed on the 2GS. It was cross-assembled on a modern-day PC. But before we can take a close look at it, let's first gather the most important facts about the 2GS. The GS has a 65816 processor, making it the only Apple II computer with 16 bits. And when you had one in 1994, it would most likely have had 4 MB of RAM and an accelerator, pushing it to 8 MHz. This is what sort of became the target platform for us. Okay, what else is there? As you know, GS stands for Graphics and Sound. Both are essential to demos. Graphics first. The 2GS has a super high-risk graphics mode with 320 by 200 pixels, 16 colors out of a total of 4096. But there's more. For each horizontal pixel line you can choose one of 16 palettes. With that, the GS can display a total of 265 colors on the screen. Or, in other words, each horizontal pixel line can only have 16 colors, but each line can get its colors from a different palette. If you swap palettes fast enough, you can have 3200 colors on the screen at the same time. Also, each pixel line can be set to 640 mode with only 4 colors per pixel. Then there is fill mode. Each pixel line can be set individually to fill mode, where the first color 0 is disabled. Where a pixel is set, the pixels to the right are filled with the same color until another non-zero pixel or the end of the line is reached. So far so good, but now on to the bad stuff. The GS has no sprite engine, so when we talk about sprites, it's just objects that we paint to the screen. There is no double buffering. This means that we have to check the beam that draws the picture and carefully update the screen accordingly. And also, no hardware scrolling. There are 32K of graphics memory in one fixed location and that's it. And if all that wasn't bad enough, writing the graphic memory is slowed down to 1 MHz. So while you normally write to memory at 2.8 MHz, which is bad enough, some genius at Apple decided to slow things down to 1 MHz. An accelerator won't help us here. Thank you, Apple. Sound. The GS has a sound chip called Insonic Dock. It is the successor to the famous Commodore 64 SID chip. It has 32 voices that can play sound to one of 8 output channels. Nevertheless, stereo output was the most common. Unfortunately, the 8-bit sample data has to reside inside the dedicated 64K sound memory. 64K is very little space. This is a bit of a headache for musicians that are used to other platforms. Now that we have established what a GS can and can't do, let's check out the Kernkompetenz demo itself. for watching. Go ahead and try it on your machine. Now, let's look behind the scenes of how this was done. The demo is basically a series of effects that run one after another. Each effect is a small program that is executed. When the effect is finished, it returns to the main program, which passes control to the next effect. The music is just playing independently using interrupts. The 2GS memory consists of banks of 64 Ks. Each effect was programmed to a fixed bank and location. Once all effects have their place in memory, a memory dump is created. Each bank is compressed using LZ4 and added to a big single file. The demo loader then reads each bank and decompresses it immediately. Back in the days of the mega demo, we wrote our own compression routine, which could decompress data in the same memory location and save memory. But for Kernkompetenz, LZ4 was the better choice. It produces way smaller output files. LZ4 makes it possible to have 3 to 4 megabytes squashed down to less than the 800K of a typical disk. Okay, let's start with the large scroll text. As I mentioned before, there is no hardware scrolling, which makes this very CPU intense. So here the choice of the logo determined the technique to use. To write the effect, it would have been much easier if there only was a thin outline to the font. But the logo that finally made it into the demo has many color gradients next to each other, which means that there are a lot of different pixels to move. So here we are using sprites to do the job. The whole logo is cut up into 4 rows of stripes which form the sprites. This is done twice. There are wide sprites which are many pixels wide and narrow sprites with only 4 pixels. These sprites are transformed into programs that draw the pixels to the screen as fast as possible. The wide sprites can better be optimized for speed, which is the reason why we need them in the first place. And because of speed, we want to use them as often as possible. So we are using the wide sprites to paint the logo across the screen and fill the left and right gaps with the narrow sprites as needed. The fastest way to paint adjacent pixels on the 2GS is by placing the processor's stack onto the graphics buffer, which is what is done here for the wide sprites. After each pixel line, the stack has to be moved. This would cost too much CPU cycles for the narrow sprites, so we just use the normal way to write to memory. A 16-bit write command places 4 pixels onto the screen. The generated sprite programs take into account that the sprites move to the left, so there's no need to erase sprites for the next frame. Okay, but why is the logo cut up into 4 rows of sprites? The reason is because the 2GS doesn't have double buffering like the Apple II. We wait until the monitor beam reaches the last pixel line. Then we start drawing the upper quarter of the screen. By the time we have finished, we draw the next quarter. That way, we make sure we stay in front of the beam. Otherwise, we would have tearing. We can visualize where the monitor beam runs by switching border colors. The red stripe at the bottom is where we draw the first quarter. Blue shows how far the beam travels while we draw the second quarter, and so on. Black is where we have finished painting. Note that the emulator here is way faster than a real GS, where there's almost no black on the screen. And finally, the name tags in front of the scrolling logo. These are also sprites turned into programs. For each sprite, we have one code that draws and one that erases the pixel. The whole effect uses 4 banks, or 265K. Enough of the intro, let's get some action on the screen. The next effect is your average 3D rock from outer space, because cubes are so out of fashion. Then there's a ring and some cubes. Anyway, how was it done? First off, we are using fill mode here to save CPU time. But as it turned out, even an accelerated GS is too slow to live calculate and paint the 3D objects. And because of the beam and the slow graphics bus, we can't draw pre-calculated lines either. Remember, we have to draw very complex full-screen objects 60 frames per second to get really smooth animations. To make this possible, we start out by using Blender on a modern-day PC. Blender is a free rendering program to create movies with 3D objects. And that's what we did. We render out pictures to our screen resolution. All shadow effects need to be disabled. By using only light sources that will give each surface a single color, we get nice images for our target platform. Where there are more than 15 colors, we use a converter to fix that. The result still looks nice. Each animation has 100 frames, and each frame is converted to fill mode. Only those pixels need to be drawn to screen. The purple pixels show where we need to draw black pixels. Now it gets difficult. For each frame, we need to store the colors and the pixels as compact as possible to save disk space and at the same time make sure that the resulting data can be compressed nicely. The ring has frames with over 1500 pixels. If we would store X, Y, and color for each pixel, we would get 450 kilobytes. That is way too much for our 800K disk. Instead, we sort all pixels by color and just store the delta X values from one pixel to another. For the most part, the delta X values will form patterns which can be compressed nicely with LZ4. Now we need a playback program for our frames. It has to be very fast and it needs to take into account that we have to draw the picture from top to bottom so that we can once again raise the beam. It's too slow to draw the frames from the compact format, so a program will rearrange the frame data inside the GS memory. It takes each frame and draws pixels in a line-based buffer, where each entry is an X value and a color byte. All we need now is a program that reads a line from the buffer and outputs the byte values to the screen according to their X. By changing the offset to where the program draws to, we can create all the effects, like the wobbling of the rock or the blurry ring. By drawing lines multiple times, we can create a vertical wobble effect. The green screen cubes is just a reverse playback of the cubes animation with alternating color palettes for each pixel line. Because of the double decompression mentioned before, the entire part of the demo takes more than 1.5 megabytes in RAM. The next effect shows the logo of the demo. The rotating object was done in the same fashion as the other 3D objects, only the color palette is fixed for all frames. Each frame of the animation is remapped to best fit the colors of the logo. Also, the program that converts the Blender output images makes sure to paint around the logo. Flooding the logo out of the screen is done by simply filling the screen with 0 pixels, starting from the right and letting the 2GS's fill mode do its job. The scrolling grid was, you guessed it, pre-calculated. It is also using fill mode. For the vertical grid bars, we generated 80 animation frames. Each frame is converted to fast draw programs that just draw one line. Calling these programs for all 200 pixels makes sure we get full screen. By going through the frames backwards and forwards, we can make the grid move left and right. The horizontal grid bars are done by simply setting the proper color palette in the corresponding lines. To save CPU cycles, the all-white area is not updated. The overlaying circles and the plasma effect are in some ways similar to the rotozoomer, so we'll skip right over them. The sprite animation is just that. Paint sprites to the screen as fast as possible. The sprites can be painted directly on the screen, except in the area of the text. For this area, we use different pre-generated sprites that pick up the foreground image before writing to the screen. The movement of the sprites is pre-calculated. Here come the pool noodles. This effect started in a vector drawing program. We used Inkscape for this. Here you can see all the paths, red, green and blue. The yellow curve is the path that the camera takes. For each path, a program was generated that paints the path from top to bottom, more than 2000 pixels high, which makes them the largest sprites that were ever done for the GS. Now the player program on the GS just needs to know where to jump into the sprite program and where to exit. Guess what? For each frame, this information is pre-recorded. All of this data is very similar, so it's ideal for the compression algorithm. All that's left is to record the information about the boxes. Granted, this effect is not very CPU intensive, but something just to enjoy. Next up is the rotozoomer. We are going into much more detail with this effect. To draw a rotated picture to the screen, we need to do the following. We set the rotation angle A. Then, for every x and y coordinate of the screen, we need to calculate the x and y into the texture. We find the pixel color of the texture and put the pixel on the screen. Then we go to the next coordinate. Of course, in memory, the texture image will be just one continuous buffer of pixels, and we really only need a pointer into the texture. This pointer can be written like this. Put that into the upper formula and we get. Now we regroup the formula's x and y factors and get this. Or simply, this is a very nice result. It means that in order to find our pointer to the texture buffer, we need to add two values that are totally independent from one another. You will see soon why this is very important. Before we go on, we have to make some decisions. The texture should be 90 by 90 pixels. We want to zoom in 3 times the original texture size. We want the angle to go from 0 to 360 degrees in 5-degree steps. This means we get 68 different values for the angle. For speed reasons, we use double pixels. 2 bytes on top of each other form 1 pixel. That means we have 160 pixels horizontally and 100 pixels vertically. But we still need to update 32K of screen buffer for every frame. First of all, to save processor time, we transform the functions into tables. Function A, for instance, has 68 values for the angle and 160 values for x. We want to zoom in 3 times, and we need 2 bytes for every value. So the size of table A for function A is 65,280 bytes, which fits perfectly into one 64K memory bank. We set up the table B for function B in the same way. Our algorithm for drawing a pixel is like this. Use the angle value to look up a pointer into the function A table. Use the angle value to look up a pointer into the function B table. For the current x coordinate, get the value from table A. For the current y coordinate, get the value from table B. Add both values. Use the sum as a pointer and look up a pixel in the texture. And draw the pixel to the xy coordinate. Now we need to do this in assembly and as fast as possible. So let's look at the table values for a given angle. As you can see, for every row, we can use the same set of values from table A in blue. The values of table B in green only change from row to row. If we write the values of table A into a self-modifying program, we can for each row run the program with the Y register taken from table B. This is the fastest way of adding two numbers and looking up values from the texture buffer. Please note that, since we are dealing with 1-byte pixels, we set the CPU to work in 8-bit mode. Now the values that we get from the texture buffer are not directly placed onto the graphics buffer, but instead are written into another self-modifying program. The second program is what draws the pixels into the graphics memory, once again using the fast stack on graphics method. Also, this draw program fits nicely in a direct page or zero page, which makes the STA commands a little faster too. Since all our pixels are doubled, we run the draw program twice to draw 2 lines of pixels. So there you have it. Of course, the IIGS, especially with its terrible slow graphics bus, is not able to update the screen fast enough, so this effect is not running at 60 frames per second. Still, Kernkompetenz is, to my knowledge, the only program on the IIGS ever that does full screen updates of every pixel. This leaves us with the final effect, the credits. By now you know how it's done. The rotating sphere is using fill mode like the other objects before, and the scrolling text is, like always, painted to the screen by pushing data onto the stack. To keep things running at 60 frames per second, we have to make sure that we only draw what changes from one frame to the next. So for instance, the white pixels between the lines of text are not painted at all. In cases where even that got too slow, we simply changed the text a little. Thanks for watching. I hope you liked the look behind the scenes. If you want to get in touch, you can reach us via the contact page of our website. Bye everyone!